All right, everybody, I'm ready to get started. Welcome back to yesterday. It's not the 26th, it's the 27th. Sorry about that. Welcome to the last day of the third to last week. So we have 2 weeks left after today. Not a lot of time. Time has flown by. I feel like I did just meet you guys. I did really just meet you guys, but now we are at the end of this journey together. Don't underestimate how quickly that time will pass these last 2 weeks. It will go by quickly. So take full advantage of every moment you have. You have this weekend, you have next weekend without that pressure of like the finals and studying for the classes. So it's a great time to just take advantage of that moment, those moments, to maybe do as much as you possibly can. Certainly knocking the paper out, as I've mentioned, is always something that should be on your mind. If you haven't already done it, I recommend that you do. I recommend that you just throw it together, get it done, get it ready. Even if you don't want to completely finish it, if you get it done now, you can give it one last pass right before the due date, and that will, maybe yield better results. Who knows? But I know you have other classes, other responsibilities. It's all going to come down at once. It's all going to happen at the same time in these next 3 weeks, papers, exams, projects, whatever. So there is no free time. Like, you don't have free time. That should be your mentality. That should just be the approach that you take from now until the very end. And once that's done, it's over. Done. Semester's over. You can reboot. You can take your mind off everything. You can just sleep for a week if you want. You can do whatever you want, but until that time comes, it's time to just be as realistic as possible about the situation that you're in. Don't run away from it. Don't be afraid of it. You signed up for it. This is the nature of the thing that you signed up for. If you commit yourself to something, you have to take it head on. If you do not take it head on, then you do not do well in it. And again, this is a training ground for you for the real world, where there aren't many second chances. Like, if you're given a task, a big one, and it requires a lot of work, you have to do it, and you have to do it well if you want to impress whomever, be it your customers or be it the people above you that can give you further opportunities. So this is the time to really, again, push yourself, grow, become the best you can, so that you have a fighting chance out there. All right, so again, the paper is due a week from Tuesday. Today we'll finish off chapter 13, and so that'll be the last mini paper available for you beyond the open chapter mini paper that's due on Sunday, I think. And so beyond that, you have all next week to get your paper finalized. I've already talked about several times how you do that. If you haven't been coming to class or listening to my lectures, just listen to the first part of the last few lectures. I've talked about a couple of times what you should do to get the paper together. Again, as far as turning it in, the digital option is available to be turned in, but the physical copy also needs to be turned in to me by the due date, a week from Tuesday. I will take them in class on that day. If you want to turn it in prior to that, slide it under my door in my office, or come to my office hours and drop it off. But make sure that you write on it that you are my 310 class, because I've got a lot of papers coming from a lot of different classes. So I need to make sure I can easily sort through the courses and give people the grade that they deserve. And that's it, I think, as far as all that goes. I'll do my best to try to grade the mini papers next week at some point, but it doesn't matter. If you've turned in the mini papers and they have met the requirements of the mini papers, which is 2 to 3 pages, and basically each one being an economic naturalist observation, you will get the full credit for them. If they do not meet the requirements for the mini papers, you will not get credit for them. So if you just, again, like I've said this at the beginning, if you just submitted something and you assume that I wasn't going to look at it, I'm going to look at it. It happens a lot. Every semester, people just turn anything in. Like, I've had people turn in like blank documents. I've had people turn in like a few words on a Word document. Like, it's pretty silly. I will not give you points for that. I will not give you points if you didn't at least meet the 2-page threshold. So I'll make sure that was the case. I was clear about at the beginning. So, and all the resources I have specify that. So anyway, yeah, so I'll try to get that done, but I'll definitely have everything graded by the final. So by the day of the final, I'll have everything graded, all your mini paper scores and the paper score, and I'll probably email you at some point prior to that telling you that you can see that score on Moodle so you have an idea of all your points going into the final. But again, this class is curved, and so it's not clear where everybody stands until the end, and so it's not it doesn't make any sense for anybody to approach me and say, what do I need on the final to get A, B, or C? Like, there's just no way to know because I don't know how the final is going to go. I don't know what the final curve is going to look like. So you guys you need to aim to do the best possible in the final. As I mentioned, the final itself is not curved, and so if you do really well on it, you can have a really big impact relative to everybody else in the class and really kind of move your way up the brackets once the final tallies are accumulated. So just aim to do the absolute best in the final possible, and that's it. If you want any type of grade in this class that you're aiming for, then that is your best option. So make sure that you do your best. But also, as I mentioned, this last part of the semester is, it is challenging in and of itself. That's why I don't make the final cumulative, and we'll further see that today. So don't underestimate the amount of time you'll need to really get all this stuff down properly. But again, it's not impossible for people to have really strong showings in the end, really strong comebacks if you're needing one, or just have a really clear sort of strong end after having demonstrated strong performance throughout the semester. Are there any questions about anything you want me to address before I move forward with the material for the day? Yeah. The final grade itself is curved, right? Yeah. Yeah, because then I would be double grade curving, which doesn't work. Yeah. Yeah, but in the end, there will be one final curve with brackets for each grade like there were for every exam. Alrighty, so this chapter, we are covering the two cases of the imperfectly competitive markets where firms compete and have market power, whereas in perfect competition, there's competition, but there is no market power. Firms aren't able to charge prices above their marginal cost. In monopoly, there is market power, but there's no competition. So these are the two in-between cases. We talked about the complexity of oligopoly and the interdependence in decision-making and how it's complicated to form any kind of clear-cut analysis about what firms should or should not do in these markets. But we have some approaches to try to figure it out given varying circumstances that firms might find themselves in. Last chapter, we covered game theory, which was a way of sort of kind of analyzing the interdependence and trying to figure out some certainty out of the uncertainty. And then in this chapter, we looked at some oligopoly models, which give us also some insights about how the markets could go and sort of the kind of outcomes we would get depending on different assumptions that are made about how the competition sort of plays out in those markets. And now finally, we'll talk about monopolistic competition that deals with the case where the firms are selling something that's very similar to what their rivals are selling. So they're selling differentiated products, but there's also a good amount of competition because there isn't a lot of there aren't barriers to entry that stop firms from entering these markets, as there are in oligopolies, as there are in monopoly. So anybody can compete in these markets, but again, it's about kind of carving out a sub-niche market by creating enough of an idea in the consumer's mind that your version of the good is better or different than the version of everybody else. So you make your product less substitutable in their minds and therefore kind of establish your own sort of demand for it, even though that demand is subject to a lot of shifts given the availability of substitutes. And so we'll kind of look at that in the most general sense first to kind of identify how firms can, maximize profits, just the standard stuff we've been doing. And then we'll look at this model. It's called the spatial model of monopolistic competition that involves looking at the trade-off between the amount of product variety that exists versus the costs of that. So like in order for there to be product variety, generally you'll have a lot of firms in markets and they won't be minimizing their average costs. So prices will generally be higher the more diversity of products there are, because again, the firms are able to carve out enough of a niche that they have some market power for their version of the good that they're selling. And so prices tend to be higher as a result of it. And so as a society, the question is like, do we need as much product differentiation, or could we be okay with less of it and have lower prices and be happy with that? So we'll kind of examine the trade-off between the two via this kind of weird model that you'll be introduced to today. But previously, let's just quickly go over some of the stuff we covered last time, just so you get one last pass on it with me before you are left to kind of figure this out on your own. So again, we covered 3 different models of oligopoly. The first one being the Kuno model, in which the central assumption is that each duopolist treats the other's quantity as a fixed number. Essentially, they are competing on quantity, on the quantity dimension. They are choosing how much they're going to supply at any given time. They choose it at the same time in the Kuno model. And so as a result of that, they have to basically take the perspective that their opponent's output is constant. So this is like the total demand for the market. If there's 2 firms in the market, then this is firm 1. They take firm 2's output as constant, and then they have what's called the residual demand, and they have a marginal revenue associated with that. And what they end up developing as a result of this situation is not a clear-cut answer to how much they should be supplying, but a decision rule that establishes how much they should supply, the quantity that they should sell, in response to how much their rivals are producing. So it's called a best response function or a reaction function, and we derived them. We went through the math to do that. If there's only 2 firms, we can graph both of their reaction functions with the quantity that firm 1 chooses on the x-axis and the quantity that firm Y charges on the y-axis. So again, this is firm 1's reaction function. This is firm 2's reaction function, telling it how it should optimally set its output in response to its rival. And these conditions lead to an equilibrium in these markets in which each firm sells a certain amount that will maximize their profits, given that they also have to consider what their rivals are doing. And so you can look at the dynamics of this. We looked at this last time where, like, if let's say there's only 1 firm operating, that means that firm 2 is not operating, and firm 1 is the only seller, so this is their monopoly output. If firm 2 were to enter the market, overcome the barriers to entry, and enter the market, then this is their best response function. So then in response to firm 1 supplying this much, they would supply this much. In response to firm 2 supplying that much, then firm 1 would respond with lowering their output and supplying this much. That would cause firm 2 to, again, in this case, increase their output, and then that would cause firm 1 to react to that. Eventually, that back and forth process would lead to this equilibrium outcome. The same process happens on the left-hand side. This process doesn't actually play out. It's just understood that it would play out, and therefore it's these quantities that are going to prevail in these markets, and it's these quantities that the firms want to solve for. And so that's what we did. We went through a couple of examples on how to do that. We looked at this other model called the Bertrand model. In the Bertrand model, the assumption here is that firms engage in price competition and react optimally to prices charged by competitors. So in this case, they essentially wind up in a price war in which they wind up undercutting each other. And so the outcome of a Bertrand oligopoly is that the firms basically wind up charging their marginal cost, earning zero economic profit. So you get the same result as you get in a perfectly competitive market. Then we looked at the Stackelberg model. The Stackelberg model is similar to the Cournot model with one difference. The difference is that there's a firm that gets to make their output decision first, and then the Cournot followers respond to that. So the followers, the other firms, react in the same way that any Cournot firm does. They have a reaction function, and it tells them how much they should supply in response to their rival. The Stackelberg leader needs to take that into consideration, the fact that their rival is going to respond in that way in order to set its own output. It does that, sets its output, and then the rivals respond to that optimally via their response function. So we talked about what that looked like. And so then we solved for all the various outcomes in the market depending on what type of competition was being engaged in. And we see that obviously in perfect competition, you get the most efficient market outcome. You get twice as much output as in a monopoly setting. We get a low market price equals marginal cost. In this example, we assumed marginal cost was equal to zero, so price was equal to zero. And of course, zero economic profits in the long run. In the Bertrand outcome, we get the exact same result. So everything's the same on this chart. In the Stackelberg, because there's a first mover advantage, we get a better outcome than if there isn't. We get 3/2, 1.5 times the monopoly output. We get half the monopoly price, and we get 3/4 of the monopoly profit. So profits are certainly bigger than down here. Output is better than up here, but obviously worse than in perfect competition. And prices are worse than perfect competition, but definitely better than monopoly. If there isn't a first mover advantage and they're choosing quantities, then we get the Cournot outcome, which lessens the efficiency of the market, lowers the amount of output produced, increases prices, and also increases profits for the firms. And then, of course, if the firms are able to collude and work together and share the market, then they work together as a monopolist, in which case they have the lowest amount of output in the market, they have the highest price, and, of course, the highest profits as well. And so here, graphically, we saw the outcomes as well. Monopoly, Cournot, Stackelberg, and Bertrand, perfect competition. All right, let's move on to monopolistic competition. So again, firms can find themselves in any one of these settings. Monopolistic competition is the next worst option from perfect competition, where you have the most amount of competition and the least amount of price control. Monopolistic competition falls under the category of imperfect competition, again, where firms do compete and also have market power, and the competitive outcome is better than in oligopoly, which tends to edge towards monopoly depending on how many firms there are in the market and the type of competition they engage in. All right, so a market structure, again, that lies between the extremes of monopoly and perfect competition is monopolistic competition. An industry is monopolistically competitive if there are many buyers and sellers. Each firm in the industry produces a differentiated product. There is free entry and exit from the industry, which is different from an oligopoly. Again, oligopolies have barriers to entry, not as severe as a monopoly to the extent where all firms are kept out, but the barriers are big enough that it keeps most firms out. And in monopolistic competition, again, the firms make kind of slightly different versions of the products. Again, you can just think of the basic example of like fast food, a Big Mac, a Whopper. They're both burgers, meat, bread, tomato, lettuce, onions, burgers. But Burger King is able to say, mine's a Whopper. And then McDonald's says, mine's a Big Mac. They're different. Pay me different amounts. And so that's sort of how it works. Like if they create that idea in consumers' minds that the products are actually different than what they inherently are, then that creates sort of a new product that allows the firm to then have their own demand for the product, which then they have market power over. So in order to profit maximize, they then therefore need to consider, again, a downward sloping demand curve, unlike, again, perfectly competitive firms that face that perfectly elastic demand curve at the market price. Monopolistic competition, when they're profit maximizing, their approach is essentially like a monopolist because, again, they have their own downward sloping demand curve. So the determination of profit maximizing price and output under monopolistic competition is precisely the same as for a firm operating under monopoly. And we get that insight from what's called the Chamberlain model, which is what we're looking at here. It's something that's mentioned in your homework. So anyway, because they face that downward sloping demand, then again they have that marginal revenue curve that's going to be less than the demand curve. That means marginal revenue will be less than price, again because of the quantity and price effects that occur when they try to sell more and lower price. If they want to sell more, they have to lower the price, which means that they don't get just the extra revenue from the extra units sold, which is what's called the quantity effect of a price change, but they also have to lower the price on existing units that we're selling, which is called the price effect. And so that eats into the revenues by selling extra units, which means that the extra revenue gained by selling additional units, the marginal revenue, is not going to be the price they get to charge on the next unit. It's going to be less than that. So that's why we have that marginal revenue less than price. Let's throw in a marginal cost curve, standard swoosh shape, increasing returns, decreasing returns. Again, they're going to set their output at the point where marginal revenue equals marginal cost. So that's where they're going to choose their output level. There's an average total cost curve there. Again, U-shaped. U happens, bottom of the U happens where marginal cost crosses it. So once they set their output level, they need to figure out what they're going to charge. They go up to the demand curve to figure that out. And then they need to figure out if they're profitable. They look at if the average total cost of production is less than the price at that quantity of output. In this case, it is. And therefore, the difference between the price and the average total cost times the quantity sold is their profit. So everything you see here is exactly like it was for monopolists. Since the firms in a monopolistically competitive industry produce differentiated products, the notion of an industry or market demand curve is not well defined. So we can't aggregate across all these individual demands. We can't say, well, the demand for the Big Mac and the demand for the Whopper, if you do horizontal summations across prices, we'll get the demand for the entire burger market. You can't really do that because the products are slightly different from each other, so they are kind of different markets, even though they do fall under the same umbrella. And so therefore you can't have that market demand curve. Quick practice problem. Suppose the inverse demand function for a monopolistically competitive firm is given by 100 minus 2q. The cost function is given by 5 plus 2q. Determine the profit maximizing price and quantity and the maximum profits. So again, you do what you always do for a monopolist. You set marginal revenue equal to marginal cost. What is marginal cost here? It's 2. Very good. What is the marginal revenue? 100 minus 4q is correct. We're doubling the slope in absolute value. Nothing has changed here. So again, there's our marginal revenue set equal to marginal cost. And then we just do some algebra here to solve for quantity. So subtract 100 from both sides, divide both sides by -4. And that gets us to 24.5 units is what this monopolistically competitive firm will be supplying. Profit maximizing price is found by, of course, plugging in our quantity into our inverse demand function to see what people are willing to pay for that quantity. And that gets us $51. And then profits, of course, are the difference between revenues and costs. Pretty simple to calculate. Price times quantity minus the total cost of producing 24.5 units, which winds up equaling $1,195.50. Not difficult, pretty standard, done it a lot of times. So really just the important thing here is to know that you do take the same approach as a monopolist when doing all of this stuff. And that simplifies the situation for you. Long run equilibrium. So remember, in the long run, in perfectly competitive industries, if there are profits, firms will enter and they will erode those profits. If there are losses, firms will exit. That'll increase the price, and the remaining firms will not be making losses. Everybody in the long run in perfectly competitive markets makes zero economic profit. In a monopoly situation, the firm is able to make profits in the long run. Firms are not able to enter the industry. Profits cannot be eroded because there are barriers to entry, which is what is what is creating the conditions for only one firm to exist. Same thing for oligopolies. Monopolistically competitive firms, slightly different. Because there are no barriers to entry. Firms can enter and exit these industries. So suppose a monopolistically competitive firm that sells brand X faces that initial demand curve. Since the demand curve lies above the average total cost curve, the firm is earning positive economic profits. This is the one we looked at a bit earlier. Because there are positive economic profits, firms will enter the industry, set up shop. In-N-Out will enter, Jack in the Box, whatever. They'll compete against Burger King and McDonald's. As additional firms enter, the demand for this product will decrease because some consumers will substitute toward the new products offered by the entering firms. So what happens when demand decreases graphically? Demand curve will shift to the left. Very good. So our demand curve will shift to the left. Entry will occur until the demand curve decreases to D1, where it is just tangent to the firm's average total cost curve. So again, we're starting off here, and then the firms will enter until the point where, at the point where marginal revenue equals marginal cost, that quantity corresponds to a price that equals the average total cost of production, in which case there will be zero economic profits. So much like in perfectly competitive markets, there are zero economic profits in monopolistically competitive industries in the long run. So again, so here is the marginal revenue curve associated with this shifted demand curve. That's the point that determines their output. Marginal revenue equals marginal cost. Going up to the demand curve, the red one, that's the price, and average total cost equals price, and so no profits in the long run. So the long-run equilibrium in a monopolistically competitive industry is characterized by the situation in the figure. Each firm earns zero economic profits but charges a price that exceeds the marginal cost of producing the good. In the long run, monopolistically competitive firms produce at a level of output such that price is greater than marginal cost, reflecting the fact that they have market power. So we have that loss of efficiency in these markets. There is deadweight loss as a result of it. But price does equal average total cost, which means that there are no economic profits in the long run. And the other thing to notice is that the average total cost of production is not minimized, which is the case in a perfectly competitive industry. In the perfectly competitive industry, price will equal marginal cost, and therefore the industry operates here in the long run. But since price is greater than marginal cost, in monopolistically competitive industries, firms don't operate at the minimum of their average total cost curve. So some economists argue that the monopolistic competition is less efficient than perfect competition because in the former case, firms do not produce at the minimum points of the long-run average cost curves. That means that firms do not take full advantage of economies of scale in production. They do not minimize their cost of producing as much as they could. There's just too many firms in the industry to enable any individual firm to take full advantage of economies of scale in production. No firm gets to become big enough to be able to then be operating at that minimum point in the average total cost curve. Some argue that this is simply the cost to society of having product variety. Like, if we want product variety, we have to simply accept this, that the production costs are going to be higher for the individual goods, and therefore prices will be higher as well. If there were fewer firms, economies of scale would be fully exploited, but there would be less product variety in the market. The relevant question is whether people who currently buy from monopolistic competitors would be happier if all products were exactly the same and cost less. So that's, again, sort of like the question central to this industry, the trade-off that we as a society should contemplate and maybe have both implicitly and explicitly. And it's one that we can analyze via this other model we're going to look at right now, called the spatial model of monopolistic competition. All right. The extent to which one monopolistically competitive firm is an effective substitute for another determines how closely their industry will resemble perfect competition. If the goods are perfectly substitutable, then everybody's selling the exact same thing. That means that in the end, nobody sees any difference in the products. You essentially have perfect competition. But again, if the firms via advertising are able to create enough of sort of a brand identity to what they're selling that will differentiate the products from each other. But there are other dimensions that one can think of to sort of characterize product differentiation. One concrete way of thinking about lack of complete substitutability is distance. So gasoline sold across town is not a perfect substitute for gasoline sold at the nearest corner, especially when your tank is nearly empty. Imagine yourself a resident of a small island nation with a large lake in the middle of it. So it's sort of like a circular island with a lake in the middle, kind of like this, but it would be completely filled out. Business activity is restricted to the donut-shaped piece of land that constitutes the island's periphery. Assume that there's considerable specialization of labor on your island. People work all day and then eat their evening meals at restaurants. Assume that you and your neighbors prefer to eat baked potatoes and grilled beefsteak every night. So everybody does different things on the island, but everybody eats the exact same meal on the island. So again, this is just a simplified world that we need to set up in order to understand what kind of insights the model can give us. So you have to think within the simplicity. So meals in any given restaurant are produced under increasing returns to scale. The more meals produced, the lower the average cost per meal. The relevant question is, how many restaurants should there be on the island nation? If the island is small, then one restaurant would be enough and keep costs and prices low. If the island is large, convenience becomes more of a priority over cost, and thus more than one restaurant would be optimal. The cost of getting to and from the restaurants then becomes a consideration. Suppose there are initially 4 restaurants equally spaced out. So suppose the circumference of the island is a mile. So this is our island here. The distance between adjacent restaurants will then be a quarter of a mile. There's 4 restaurants represented by these green squares. Then that's 4. Then they would be equally spaced, and therefore there would be a quarter mile between them. No one can live more than 1/8 of a mile away from a restaurant. So the furthest anybody can live away from a restaurant is exactly in between 2 restaurants, right? So that's the furthest someone would live from a restaurant. Suppose that there's L number of consumers scattered uniformly about the circle. So uniformly, they're not concentrated in one part of the island, they're uniformly scattered throughout the island. The cost of travel is $T per mile. So there's a cost to traveling to and from restaurants, and it is $T per mile. If T were equal to $24 a mile, and the average distance from the restaurant is, let's say, a 1/16 of a mile, which is the average between being exactly at the restaurant and the furthest away from a restaurant. So again, 0 plus 1/8 divided by 2 is 1/16. So that's the average distance to a restaurant. Then the cost of a round trip ticket, 2 times the distance, which is, again, 2 times 1/16, would equal, so you have 2 times the distance times the dollars per mile. So 2 times 1/16 times 24. So in this case, under these assumptions, the average transportation cost per person to go to a restaurant and eat a meal would be about $3. Suppose further that each consumer will eat exactly 1 meal a day at the restaurant for which the total price, and the total price is the price of the restaurant meal plus the travel cost, is the lowest. Lastly, suppose that each restaurant's total cost is represented by a cost function where there is some fixed cost and some variable cost. F is the fixed cost, M is a constant marginal cost. If you take the derivative here, you get just M. And Q is quantity. So the average total cost is thus, this is our total cost, so the average total cost is going to equal then total cost divided by quantity. So you've got F divided by Q plus M, implying that the average total cost will decrease as there are more meals sold. So again, there are increasing returns to scale, economies of scale to producing meals on this island. Suppose that each of the 4 restaurants have the same cost function. They have the same cost, and there's 100 people on the island. Then each restaurant obviously will serve 100 divided by 4. There's 4 restaurants, so that's 25 meals per day. And its total cost will be whatever it is to supply 25 meals, which is 50 plus 5 times 25, which equals $175. So the average total cost, the average cost per meal on the island to produce would therefore be 175 divided by 25 people per restaurant, which is $7 per meal. So that's our average cost of a meal, $7. And then we've got the average transportation cost, which is $3. So the overall average cost per meal is then equal to the average total cost per meal plus the average transportation cost, which equals $10 per meal. I have a typo there. I never noticed that. All right. The optimal number of locations then. So now that we have that information, we can solve for the optimal product variety. How many restaurants is optimal for the restaurant? We've solved right now for the situation where there's 4 restaurants. So the optimal number of locations is the result, again, of a trade-off between the startup and other fixed costs, how much it costs to provide additional restaurants, and the savings from lower transportation costs on the other, right? So if people feel that the transportation costs are too much to go to these faraway restaurants, then they will be willing to pay more money for restaurant meals if they can lower their transportation costs by having additional restaurants on the island. So the best way to assess the optimal number of locations is to check if the average overall cost per meal is declining with increased locations. And when we say average overall cost, we're talking about the overall cost of a meal, including transportation costs. So suppose the number of restaurants in the last example increased from 4 to 5. Each of the 5 restaurants, in this case, again, have that same cost function. There's still 100 folks on the island, so each restaurant will serve, in this case, 20 meals per day. And its total cost will be $150. And that means the average total cost in that case will be 150 divided by 20, which is $7.50. The distance between restaurants will now be 1/5 of a mile. The longest distance to a restaurant is half of 1/5, which is equal to 1/10. So again, that's the midpoint between 2 restaurants. Multiplying the distance by 1/2 to take into account the average of the longest and the shortest distance, either a person living right next to a restaurant or exactly between 2 restaurants, is 1/20th of a mile. The cost to travel is still $24 a mile. So the round trip in this case will cost, again, 2 times the distance times the transportation cost, which is, in this case, 2 times the 1/20th of a mile times 24, which is $2.40. The average overall cost of a meal is going to equal then $7.50 plus the $2.40, which is $9.90. So we can see that the average cost per meal does go down when increasing restaurants from 4 to 5 meals. So therefore, it does make sense to have an additional restaurant. So product variety is increased, and the costs that are being saved are worth it to the customer. Like, even though they're paying more for meals, they're saving more in transportation costs. So if we perform the same analysis with 6 restaurants, we would see that the cost increases per the overall average cost of a meal increases, making 5 the optimal number of outlets. All right, now let's look at the most general case. So more generally, if there are n outlets around the loop, the distance between the adjacent outlets will be 1 divided by n. Again, we're assuming that the whole represents 1 mile. The maximum one-way trip length in this case will be 1/2 of 1n. So again, 1 over n tells us the amount of the distance between restaurants, and therefore this is the furthest distance from a restaurant, which is 1 over 2n for any given person. Assuming folks, again, are uniformly distributed throughout the loop, the average one-way distance to the nearest outlet will be, again, this plus 0 divided by 2. So it's going to equal 1 over 4n. So that's the average distance to a restaurant. So the average round trip will be twice that. So 1 over 2n in this case. Since the distance between the restaurants declines as the number of restaurants grows, the total transportation cost will be a decreasing function of the number of outlets, which you would expect, right? More restaurants means less travel time. Travel costs go down as more restaurants are put up. Since transportation costs is $T per person per mile traveled, the total transportation cost will again be a product of the cost per mile times the population times the average round trip length, which is 1/2n. So that is our cost of transportation function. Again, it is a decreasing function of the number of restaurants. As restaurants go up, it brings the transportation cost down. The total cost per meal served, C meals, also depends both on population and the number of outlets. So in this case, we're going to have the N represents the number of outlets times the fixed cost. So there's going to be a certain amount of restaurants, and each one of those restaurants will require a fixed cost to set up. And then there will be a certain amount of meals sold, which is 1 per person. So L people will buy meals. And then the cost of each of those is the marginal cost, which is constant. So the object is to choose N to minimize these combined costs. So again, there's our transportation costs, there's our meals, and this is the entire relationship that we're looking at. All right, so here we have 3 different curves plotted. Here is the cost of meals, here is the transportation cost, and here is the combined cost. The slope of the meals curve is equal to F. So if you take the derivative of the cost of meals with respect to quantity, with respect to N, sorry, then that tells us that the marginal cost of having an additional restaurant is equal to the fixed cost. So we know that that's constant, and therefore the slope of our meals curve is constant, so the meals curve is just a line, and we see that the cost of providing meals increases as more and more outlets are produced, because again, they sell less, and so their average cost of production is going to be higher, so they're going to charge higher. So again, that's highlighting the nature of like the equilibrium for monopolistically competitive industries, where they do wind up producing less output than they would to minimize costs. The slope of the transportation curve is equal to the derivative of our transportation costs with respect to N. So this is 1/2 times N to the -1. So multiplying that by -1, subtracting 1 from that, you're left with 1/2n squared. And there's a negative out here. So this is a derivative of, again, the transportation cost. So again, this is the slope of the transportation cost curve, and it basically represents the extra savings from additional restaurants, right? There's additional restaurants, there's savings from the amount that people have to travel and spend to travel to restaurants. And so we see that those savings, and those savings in this case are an absolute value for the slope. So therefore the savings are bigger than the cost over this range. Even after this range here, the slope is still bigger in absolute value than the slope here. So basically, again, the savings are bigger than the cost of additional restaurants up until this point where they're both equal. At this point, the slopes are equal, meaning the marginal cost of an additional meal is equal to the marginal savings of an additional meal. And then beyond that, the marginal cost of additional meals will increase high, and it will be bigger than the savings for from not having to drive as far. All right, so if the slope of C meals, again, is less than the absolute value of the slope of C trans, the reduction in transportation cost from adding another outlet will more than compensate for the extra fixed cost from adding that outlet. The optimal number N star is the one for which the slope of C meals and the slope of C trans curve in absolute value are the same. And we can solve for that mathematically by taking the derivative of our entire overall cost expression here with respect to the number of restaurants. So doing that will get us to, again, negative TL times 1 over 2n squared, which I did earlier, plus the only other term here with n is this one, so plus f equals 0. And then if we setting it equal to 0, we can then solve for the optimal number. So we can subtract f from both sides, which gets us to this expression here. Then I can multiply both sides by n squared, divide both sides by f. That gets me here, and then I can just solve for n by taking the square root of both. All right, so what this expression tells me is that if the transportation costs increase in this environment, then the number of restaurants will increase. So the product variety will increase if the cost to the consumer of getting the product is high enough or increases. If L increases, if the number of people increases, then the optimal amount of product variety will also increase. If the fixed cost of creating more product variety increases, then the optimal number of restaurants, the optimal amount of product variety will also decrease. Applying this result to the restaurant example, in which L equals 100, T equals 24, and F equals 50, we get 4.9, which is basically what we solved for earlier just by going through the numerical example that we went through. Rounding the realistic 5 number of restaurants reveal the answer we attained via our earlier analysis. The question then becomes whether or not the independent actions of private profit-seeking firms will result in the optimal number of outlets around the loop. So this is like a way for us to sort of identify an optimal amount of product variety, in this case, very specific to what we're looking at. But this approach can be applied to different type of markets, which I'll look at a couple of examples in a second. But the question is like, if left up to their own devices, left up to the sort of guiding of the invisible hand that Adam Smith told us about, that basically represents all the agents in the economy acting to benefit themselves, will that give us the optimal amount of variety, or will that give us more than we need? So that's ultimately a question that needs to be addressed often when we're talking about this issue. Any environmental change that leads to a change in the optimal number of outlets, here any change in population density, transportation costs, or fixed costs will lead to a change in the same direction in the equilibrium number of outlets. All right, let's look at a quick economic naturalist kind of to reflect some of these ideas. The question is, why are there so many fewer grocery stores in most cities now than there were in the 1930s? And why do residential neighborhoods in New York City have more grocery stores than residential neighborhoods in Los Angeles? So grocery retailing, like other forms of retailing, is characterized by strong economies of scale, decreasing average total costs. It thus confronts the usual trade-off between direct production costs on the one hand and the transportation costs on the other. So that trade-off we were just talking about applies here. Throughout this century, changing patterns of automobile ownership have affected the pattern of grocery store size and location in the U.S. In 1920, most families did not own cars and had to do their own shopping on foot. In terms of our expression that we solved for, this meant that we had a high transportation cost because walking takes a lot of time, and that carries an implicit cost, right? The opportunity cost of that time. Of course, today, virtually every family has a car, which has led people to take advantage of the lower prices that are possible in larger stores. One exception to this pattern is Manhattan. Most folks in Manhattan do not own a car, and the population is enormous. So L is high. We have a high L, and we have a high T, which means we're going to have a high N. And that's why we're going to have more grocery stores per block in Manhattan than you're going to see in Los Angeles. Manhattan residents have to walk more than 2 blocks to get to their nearest grocery store. The total population in Los Angeles is very high, but it is spread out over a much larger area, and most families own at least one automobile. All right, let's do a quick practice problem just to once again highlight how this whole thing works and how you can identify optimal product variety in a particular context. So in this case, we're going to look at a toll road and the number of garages that should exist along this toll road. So Toll Road Commission is planning to locate garages for tow trucks along a 100-mile circular highway. Each garage has a fixed cost of $5,000 per day. Towing jobs are equally likely along any point of the highway, and the cost per mile is $50. If there were 5,000 towing jobs per day, what number of garages would minimize the sum of the fixed cost and the towing cost is the question. All right, so we're going to let n equal the number of garages. That's what we're solving for. The distance between any two adjacent garages will be that 100 miles divided by n. The furthest a car can be stranded from a garage is going to be equal to 100 divided by n divided by 2, or times 1/2, which equals to 100 divided by 2n. So that's the furthest any car could be stranded from a garage. The closest a car can be stranded from a garage is 0. So the average towing distance is equal to 0 plus 100 over 2n divided by 2. That's going to equal 100 divided by 4n. The average round trip distance to a garage is equal to that average distance to the garage times 2, which is, again, capturing the fact that it's going to be driven to and from that distance. And the direct towing cost is equal to the average towing distance, 100 over 2n, times the cost per mile, which is 50, times the number of towing jobs per day, which is 5,000, which is the same as like the number of people on the island before. So the average towing distance times the cost per mile times the number of towing jobs per day equals 12,500,000 divided by n. The cost of garages is the fixed cost of garages times the number of garages, which is equal to n. So 5,000 times n. So the overall total cost of a garage is equal to the direct towing cost plus the garage cost. So the direct towing cost is equal to 12,500,000 divided by n plus the garage cost, which is equal to 5,000 times n. To find the optimal number, n, we take the total derivative of this cost and set it equal to 0. So again, this is n raised to -1. So you got -1 times n raised to -2, which leaves us with negative 12,500,000 over n squared plus 5,000 there. Set that equal to 0 to figure out the optimal amount of n, right? Subtract 5,000 from both sides, and then switch these two around, n squared, and then divide that, and then get the square root of that, which is equal to 50. So 50, under these circumstances, is the optimal number of garages that should exist along this 100-mile circular road that the Toll Road Commission should set up. All right. The analogy to product characteristics. So the power of the spatial interpretation of monopolistic competition is that it can be applied not only to the geographic location, but also to a variety of other product characteristics. So consider, for example, the various airline flights between any two cities on a given day. People have different preferences for traveling at various times of the day, just as they have different preferences about where to eat or shop. People will tend to select the alternative that lies closest to their most preferred option. In terms of our spatial model, having to wait for a flight is the analog of having to travel to a store to get a meal. So then the question is, why not have a flight every 5 minutes so that no one would be forced to travel at an inconvenient time? Well, obviously there's a trade-off there, the cost of the extra flight against the savings to the individuals in terms of opportunity costs of not having to wait for an inconvenient flight. So again, the answer has to do with the trade-off between cost and convenience. The larger an aircraft is, the lower its average cost per seat. If people want frequent flights, airlines are forced to use smaller planes and charge higher fares. Conversely, if people didn't care about when they travel, then the airline could use a really huge aircraft and fly at whatever interval was required to accumulate enough passengers to fill those planes. But most passengers have schedules to keep and are willing to pay a little extra money for conveniently timed flights. So we could use the same spatial model to solve for the optimal number of different flights over a given day, given the same kind of information that we've been considering. We won't do that, but you could. The model is very flexible and applicable to most contexts. All right, let's address the issue of paying for variety. Again, because there is more variety, we end up paying more for the goods that we buy. Prices tend to be higher. So variety is costly. Many critics claim that market economies serve up wastefully high degrees of product variety. The extra cost of product variety may indeed seem an unnecessary burden imposed on consumers who neither desire nor can easily afford it. In a slightly more detailed model of spatial competition, these problems appear much less serious. In our simple model, we assume that each buyer faced the same unit transportation cost. So we assumed everybody had the exact same cost. That's obviously not the same in our world. The assumption is unrealistic. Even in models where the only dimension of variety is geographic location, buyers who own automobiles will have lower transportation costs than those who don't. Buyers whose time is worth little, those that are unemployed, have lower transportation costs than those whose time is more valuable, like lawyers, doctors, people who are employed, in terms of opportunity costs, in terms of their implicit cost. The issue is the same for product variety. Those who care a lot about special product features will have higher transportation costs than those who do not, which means simply that people in the former group are willing to pay more than others for a product whose special features suit their particular taste. So throughout our society, there's people that are willing to pay more than others. It is also true that the demand for variety increases sharply with income. People are willing to pay more for variety as they become richer. The association between income and the demand for variety plays a pivotal role in the way that most producers market their products. Consider the array of automobiles offered by General Motors, ranging from the subcompact Chevrolet Aveo to the full-size Cadillac. All these cars incorporate a variety of specialized features which are the result of costly research and development. So that's one cost that firms obviously have to incur to produce product variety, research and development. The research and development costs are largely fixed, which gives rise to a substantial scale economy in the production of cars. That, again, means lower average cost of production as one produces more. If GM or any other company could sell more cars in a given year, it could produce each of them at a lower cost. When marginal cost lies above the average cost, it's not possible to charge each buyer a price equal to marginal cost and still earn a normal profit, which means that prices should be higher. If some buyers pay prices below average cost, other buyers need to pay prices above it. So the car manufacturer's response to this situation is to set the prices of its better models higher than the pricing of its lower models. The marginal costs of Chevys are slightly lower than that of Cadillacs. Since buyers who care more about variety are willing to pay more for a Cadillac than a Chevy, the company could set different prices on the two. So again, they engage in price discrimination, but really it's not price discrimination. They're not selling the same good at different prices. They're selling slightly different versions of the same good at different prices to different consumers who have different willingness to pay. The poorer consumers versus the more wealthier consumers who are willing to pay more for the product variety. So what firms engage in is what's called cross-subsidization, where they essentially, for the less varied models, the less sort of complicated versions of their products that cost them less to produce, they sell those at a really low cost, sometimes below the average cost of production. And then for the models that are more complicated, that require more research and development, that are more expensive to produce, they end up charging prices above their marginal costs, above their average total cost, more than they would normally do in order to then compensate for the loss or the partial loss that they're experiencing in the least expensive product variety brands that they're selling. So in an average year, the surplus of total revenue above variable cost for all models, which is the sum of the two shaded triangles, is just about enough to cover the company's research and development and other fixed costs. So in the end, the increased product variety is generally paid for the more wealthy people in our society, is really what it comes down to. So similar pricing strategies affect recovery of the cost of variety in virtually every industry. All right. And finally, let's look at this last situation, which is kind of interesting. It's called Hotelling's hot dog vendors, and it kind of highlights the fact that left up to their own devices, that firms don't always make the best choices, and therefore product variety may actually wind up not being as varied as it should be. So in Harold Hotelling's seminal paper on the spatial model of monopolistic competition, he discussed the problem of two hot dog vendors who are free to position themselves wherever they wish along a stretch of a beach. Suppose the beach is a mile long and it's bounded at each end by some natural obstacle, rocks, ocean, whatever. Suppose also that the vendors charge the same price. Customers are evenly distributed along the beach, and each customer buys one hot dog from the nearest vendor. If the vendor's goal is to sell as many hot dogs as possible, where should they position themselves is the question that we are considering. So suppose that vendor 1 stands at some point A and vendor 2 stands at some point B, where both A and B are a quarter mile from the midpoint of the beach located at C. All customers to the left of C are closest to vendor 1 and will buy from him. So everybody over here obviously will buy from A, while those to the right of C will obviously buy from B. With this configuration, the two stands get half the hot dog market. The greatest one-way distance any customer has to travel is a quarter of a mile, and the greatest distance, the greatest average distance is therefore 1/8 of a mile. Again, the furthest 1/4, closest 0, divided by 2, 1/8. So A and B are the locations that minimize the average travel distance for all consumers, but actually wind up not being the optimal locations for the vendors. So vendor 1, vendor A, will maximize his sales by positioning himself as close as possible to vendor 2 on the side of vendor 2 that is closer to the center of the beach. So vendor A realizes that if they put their hot dog stand somewhere over here, then they'll not only get all of their customers, but they'll get some of B's customers as well. Vendor 2, of course, can reason in the same fashion. So his strategy will be perfectly symmetric. He'll want to do the exact same thing. He'll figure out that putting his hot dog stand over here will get him more business. When both vendors behave in this fashion, the only stable outcome is for each to locate themselves in the center of the beach at C, exactly next to each other. That's the only way that they can avoid either of them cannibalizing their customers from them. So at C, each gets half the market as when they were in their original positions, but the average distance that customers must travel is now a quarter mile, twice what it was when the vendors were located at A and B. Having both vendors at the middle of the beach is thus not optimal from the vantage point of customers, and yet neither vendor would be better off if he were to move unilaterally, move on their own. So the hot dog vendor location problem is thus not one of those cases in which Adam Smith's invisible hand guides resources so as to produce the greatest good for all. So we see here that left up to their own devices, that the firms will behave in this way, which is not optimal for consumers, and therefore in this case, they actually minimize the product variety, right? Because the consumers are essentially left with only one option, which is why oftentimes, most of the time, like you'll go anywhere, malls, etc., and you will see very similar stores positioned very closely next to each other, and it's all sort of reflective of Hotelling's dilemma, like this very clear sort of result that plays itself out all the time in our world, and it doesn't necessarily make sense. Like you go somewhere, it's like, why are there two music stores right next to each other? Why are there two grocery stores on the same block? That kind of thing, like gas stations right next to each other. And the reason is because of this silly situation. So ultimately, again, like there are more issues at play when it comes to product variety. Firms aren't always going to optimally choose their product variety, and there is, again, that trade-off between having more product variety versus paying less for things. So it's a complicated issue, but it's one that is part of our world, and it's interesting. Anyway, we're done with this chapter, folks. Congratulations. 3 chapters to go, actually, and we may actually finish one day early, so we may not have class in this class that last Thursday of the week, but I'll tell you guys when we get to it. All right, everybody, you guys have a good weekend, and I will see you guys on